Somewhere in the outer darkness of the solar system, beyond the familiar worlds, beyond the red dust of Mars and the great storm systems of Jupiter and the magnificent rings of Saturn, there is a planet that does something no other world in the solar system does. It rolls. Not spins the way every other planet spins, rotating upright, or nearly so, their poles pointing roughly toward the sky and their equators sweeping through space in the plane of their orbits. Not tilting slightly, the way Earth tilts at 23.5 degrees to give us our seasons, or the way Saturn tilts at 27 degrees, or even the way Mars tilts at 25. Rolling on its side, its poles pointed not toward the sky but toward the sun, its entire axis tilted at 98 degrees to the plane of its orbit, so extreme that if you placed it next to the other planets in a line, it would look like it had simply fallen over and never gotten back up. This is Uranus, the seventh planet from the Sun, the one that textbooks tend to describe in a single paragraph between more dramatic entries, the one that gets fewer headlines than Jupiter's storms or Saturn's rings or Mars's ancient riverbeds, the one that most people, if asked to name the strangest planet in the solar system, would probably not choose first. They would be wronged. Uranus is the strangest planet in the solar system. Not in the casual sense, not the way you might call an unusual cloud formation or an odd coincidence strange. Strange in the scientific sense. Strange in the sense that professional planetary scientists, people who have spent careers studying the 8 worlds orbiting our sun, consistently describe Uranus as the most anomalous, the most unexpected, the most difficult to fit into any simple model of how a planet should behave. It rolls through space on its side. Its magnetic field is not centered on its core but offset dramatically to one side, tilted at 59 degrees to its rotational axis, a configuration so unusual that scientists are still debating what produces it. It is the coldest planet in the solar system, despite not being the farthest from the sun. It emits almost no internal heat, unlike every other giant planet, which radiates significantly more energy into space than they receive from the sun. Its rings are among the darkest objects in the solar system, nearly invisible against the black of space, discovered not by anyone who was looking for them, but almost by accident. Each one of these facts, taken alone, would make Uranus interesting. Taken together, they make it extraordinary. And yet, for most of its history, Uranus has been overlooked, passed over, considered the quiet, featureless, unremarkable member of the outer solar system, the planet that Voyager 2 flew past in 1986 and found, to the mild disappointment of some mission scientists, to be almost completely devoid of visible surface features. A smooth, pale blue-green ball, serene and apparently simple. That apparent simplicity, it turns out, was concealing one of the most genuinely strange planetary environments known to science. William Herschel did not intend to discover a planet. On the night of March 13, 1781, the German-born British astronomer was conducting a systematic survey of the sky from his home in Bath, England, methodically cataloging stars, measuring their positions, doing the patient observational work that occupied most of his professional life. When his telescope passed over a faint object in the constellation Gemini, he noticed something that a star should not do. It appeared as a disk, not a point of light like every other star in the sky, but a tiny, resolved disk, an object with visible extent, small enough to be easily mistaken for a star but large enough under careful scrutiny to have measurable size. Herschel initially concluded he had found a comet, unusual, certainly, but comets were not unknown, and a fuzzy extended object moving against the background stars was a more conventional discovery than a new planet. He reported it to the Royal Society as such. But the object's motion was wrong for a comet. Comets follow elongated elliptical orbits, swinging close to the sun and back out again in trajectories that are visibly eccentric. This object moved in a nearly circular orbit, slow, steady, distant. The more astronomers studied it, the more the orbital mathematics pointed to a single, unprecedented conclusion. It was a planet. The first planet discovered in recorded human history. Every other planet visible to the naked eye, Mercury, Venus, Mars, Jupiter, Saturn, had been known since antiquity, observed and named and incorporated into human mythology and cosmology long before the first telescope was built. Nobody in the entire history of civilization had discovered a planet before. Nobody had needed to. Now someone had. The discovery doubled the known size of the solar system overnight. If Uranus was orbiting at the distance its orbital period implied, approximately 19 astronomical units from the Sun, nearly twice Saturn's orbital distance, then the solar system was far larger than anyone had understood. The boundary of the known had been pushed outward in a single night, not by a mission or an expedition or a lifetime of directed searching, but by a careful observer who happened to point his telescope in the right direction. What Herschel had found, though he could not have known this at the time, was not simply a new planet. He had found one of the most physically anomalous objects in the solar system, an ice giant, a category of planet that had not yet been named or defined, a world whose interior is fundamentally different from the gas giants Jupiter and Saturn, composed not primarily of hydrogen and helium, but of water, methane, and ammonia in states of matter that do not exist naturally anywhere on Earth. A world whose appearance of calm simplicity conceals an interior under pressures so extreme that carbon may rain downward through the planet's depths as literal diamond rain, falling through an ocean of water and ammonia beneath clouds of methane tens of thousands of kilometers above any solid surface. A world that rotates in a way that gives its poles each 42 years of continuous sunlight, followed by 42 years of continuous darkness, seasons so extreme that they have no parallel on any other world in the solar system. A world whose moons are named not for mythological figures, as the moons of most planets are, but for characters from the works of William Shakespeare and Alexander Pope, Titania and Oberon, and Miranda and Ariel and Umbriel, a cast of literary names orbiting a world that has never quite fit the category science has tried to place it in. The strangeness goes deep, not just skin deep, not just the axial tilt, not just the color, not just the dark rings. Deep into the physics of the interior, deep into the magnetic field that wraps the planet in a configuration unlike any other in the solar system, deep into the mystery of why a planet as large as Uranus radiates so little of the internal heat that every comparable world releases steadily into space. Over the next few hours, we are going to go there. Not to the simple, easily summarized Uranus of a brief encyclopedia entry, to the actual world, the anomalous, defiant, sideways-rolling world that has challenged every model of planetary formation and structure that scientists have tried to apply to it. The world that Voyager 2 glimpsed in a few hours of closest approach, and that has fascinated and puzzled planetary scientists in the 4 decades since. The world whose interior may contain phenomena, diamond rain, superionic water, exotic states of matter that require extreme laboratory equipment to replicate, that are, in their quiet way, as extraordinary as anything in the solar system. We are going to begin at the beginning, with how Uranus formed, and how it came to be so different from every other world it formed alongside. Because Uranus was not always this strange. It did not begin tilted on its side, rolling through space in defiance of everything the other planets do. Something happened to it, something enormous and violent, and so long ago that the evidence for it is written not in any surface feature or atmospheric layer, but in the fundamental orientation of the planet itself. Something struck Uranus, and what that impact left behind is the strangest planet in the solar system. Before Uranus existed, before any planet existed, there was a moment of extraordinary stillness. Not the stillness of empty space. Space is never truly empty, not in any region of the galaxy where stars have formed and lived and died, and scattered their remains into the interstellar medium, but a stillness of potential, a vast, slowly rotating cloud of gas and dust, seeded with the elements forged in stellar interiors across billions of years of cosmic history, drifting in the outer spiral arm of the Milky Way, waiting for the perturbation that would set everything in motion. That perturbation came. Perhaps a nearby supernova sent a shockwave through the cloud. Perhaps the accumulated gravitational influence of the galaxy's spiral arm structure was enough. Whatever the trigger, the cloud began to collapse, slowly at first, then faster, drawn inward by its own gravity, spinning up as it contracted the way everything in the universe spins faster as it pulls itself together. At the center, a star ignited, our sun. Around it, the remaining material, everything that had not fallen into the growing star, spread into a flat, rotating disk. A protoplanetary disk, thin at the edges and thicker near the center, rich in dust and ice and gas, orbiting the newborn sun in a slow and stately procession that would, over the next few tens of millions of years, become the solar system we know. This is where the story of Uranus begins, not at its current position in the outer solar system, nearly 2 billion kilometers from the sun, somewhere closer, somewhere warmer, somewhere the conditions for building a giant world were subtly but significantly different from the cold, distant region it now calls home. To understand what Uranus is made of, and why it is fundamentally different from Jupiter and Saturn, you need to spend a moment with the protoplanetary disk and the way it varied with distance from the young sun. Close to the sun, in the region where the rocky planets would eventually form, temperatures were high. Too high for water ice, for methane ice, for ammonia ice to survive in solid form. The material available for building planets in the inner solar system was restricted to the refractory substances that could withstand the solar heat: silicate rock, iron, nickel, other metals and minerals with high melting points. The result was small, dense, rocky planets: Earth, Mars, Venus, Mercury. Farther out, beyond what planetary scientists call the frost line, a boundary in the early solar system lying somewhere around the current orbit of Jupiter, beyond which temperatures were low enough for water ice to condense into solid particles, the situation was dramatically different. Ice was abundant, and ice, added to the rocky and metallic materials already present, provided an enormous additional reservoir of solid material for planet formation. Jupiter and Saturn formed in this ice-rich region, accumulating solid cores rapidly, and then, because their cores grew large enough quickly enough, capturing enormous quantities of hydrogen and helium gas from the surrounding disk before the young sun's radiation dispersed it. The result was gas giants, worlds dominated by hydrogen and helium, their rocky and icy cores buried beneath layers of gas so thick that the cores represent only a small fraction of the total mass. Uranus formed differently. Uranus is not a gas giant. This distinction matters more than it might initially appear, and it is worth pausing on. The conventional classification of the solar system's large outer planets places Jupiter, Saturn, Uranus, and Neptune together as the 4 giant planets, implying a fundamental similarity of type. But Uranus and Neptune are, in their internal composition and structure, fundamentally different from Jupiter and Saturn in a way that the word giant obscures. Jupiter and Saturn are composed primarily of hydrogen and helium, the 2 lightest elements, the most abundant in the universe. Their interiors are almost entirely hydrogen in various exotic states, from the molecular hydrogen of the upper atmosphere to the liquid metallic hydrogen of the deep interior, where pressure is sufficient to strip electrons from hydrogen atoms and allow the remaining protons to flow freely, conducting electricity and generating the powerful magnetic fields these planets are known for. Uranus's interior contains far less hydrogen and helium. Its dominant constituents are what planetary scientists call ices, not because they are necessarily solid, but because they are compounds formed from elements heavier than hydrogen and helium that were present as ice in the outer protoplanetary disk. Water, H2O. Methane, CH4 ammonia, NH3. These compounds, under the extreme pressures of a planetary interior, behave in ways that bear no resemblance to the ice you might put in a glass of water. They become fluids of extraordinary density and electrical conductivity, existing in states of matter that have no everyday analog. This is why Uranus and Neptune are now classified as ice giants, a distinct category of planet, different in composition and internal structure from the gas giants, representing a type of world that appears, from exoplanet surveys, to be among the most common types of large planet in the galaxy. Understanding Uranus, therefore, is not merely an exercise in understanding one unusual planet in our own solar system. It is an exercise in understanding a planetary type that may be extraordinarily common throughout the universe. But how did an ice giant form in the outer solar system? The process was slower and more difficult than the formation of Jupiter and Saturn, and this difference in formation history may be directly responsible for some of Uranus's strangest characteristics. In the outer solar system, beyond Saturn's orbit, the density of solid material in the protoplanetary disk was lower than in the regions closer to the Sun. Planetesimals, the building blocks of planetary cores, were more widely spaced, collisions between them were less frequent, and the process of accumulating mass proceeded more slowly. The core of what would become Uranus grew, but it grew slowly. Pebbles and boulders and larger bodies collided and merged over tens of millions of years, building a solid core of rock and ice that eventually reached perhaps 10 to 15 times Earth's mass, large enough to begin gravitationally capturing gas from the surrounding disk, but not large enough to capture it in the enormous quantities that Jupiter and Saturn accumulated. By the time Uranus's core was large enough to capture substantial amounts of hydrogen and helium, the young sun's radiation had already begun dispersing the disk's gas. The window for becoming a true gas giant had closed. Uranus captured some hydrogen and helium. They are present in its outer atmosphere, but not enough to bury its icy interior under kilometers of gas. The ice-rich core remained dominant, defining the planet's composition and setting it apart from the gas giants that had formed more quickly in the denser inner regions of the disk. There is something else about Uranus's formation that has become increasingly significant in recent years. Uranus may not have formed where it currently orbits. The current leading models of solar system formation, particularly the framework known as the NICE model and its subsequent refinements, suggest that the early solar system was a dramatically different and more chaotic place than the orderly arrangement of planets we know today. The giant planets did not form in their current orbital positions and stay there. They migrated, driven by gravitational interactions with the disk of material surrounding them and with each other. Jupiter, Saturn, Uranus, and Neptune moved through the early solar system in a complex gravitational dance that reshaped the orbits of everything around them. In some versions of these models, Uranus and Neptune formed closer to the Sun than they currently orbit, in a region of the disk where solid material was more abundant and their cores could grow more quickly. Gravitational interactions with Jupiter and Saturn then scattered them outward to their current positions in the outer solar system. In other versions, Uranus and Neptune formed roughly where they are now, but their formation was influenced by the migration of Jupiter and Saturn, which scattered solid material outward and inward in ways that affected the growth of all the outer planets. The details of exactly how Uranus arrived at its current position and how its formation proceeded are still being worked out. Computer simulations of the early solar system are extraordinarily complex, and the specific history of any individual planet depends sensitively on the initial conditions and the specific sequence of gravitational interactions that occurred during the chaotic early period. What is clear is that Uranus's formation was not simple. It was not the straightforward accumulation of a core followed by gas capture in a static disk. It occurred in a dynamic, evolving system where planets were moving and interacting and reshaping the disk as they grew, a process whose complexity we are still working to fully understand. By the end of the formation period, perhaps 50 to 100 million years after the solar system began, Uranus had taken its basic form, a world of perhaps 14 times Earth's mass, with a rock and ice core surrounded by a deep mantle of exotic high-pressure ices and a relatively thin outer envelope of hydrogen and helium. A genuine ice giant, orbiting the Sun at a distance that placed it in the cold outer reaches of the solar system, where it would spend the next 4.5 billion years. At this point in its history, Uranus may have looked different from today. Its axial tilt, that extraordinary 98-degree roll that makes it unique among the planets, may not yet have been established. It may have been rotating more normally, its poles pointing roughly perpendicular to the plane of its orbit, its seasons cycling in a way broadly similar to other planets. Something was coming that would change all of that. Something large, something moving fast, something that would strike the young Uranus with enough force to permanently alter its orientation, knocking it sideways into the rolling configuration it maintains to this day, writing the tilt into its structure so deeply that 4.5 billion years of subsequent evolution have not erased it. The collision that would make Uranus the strangest planet in the solar system was still in the future. But not for long. There is a moment in the history of every planet that defines it. Not the moment of its formation, the slow, patient accumulation of dust and rock and ice that builds a world over tens of millions of years, is not a moment but a process, gradual and distributed across time in a way that resists the idea of a single defining event. Not the moment it settles into its orbit, or the moment its atmosphere develops, or the moment its interior differentiates into layers of differing composition. For Uranus, the defining moment was a collision. A single event, violent and brief on any geological timescale, that permanently altered the orientation of an entire planet. That took a world rotating in a broadly normal configuration and knocked it sideways, not slightly, not by a few degrees that might be explained by the accumulated gravitational nudges of neighboring planets over billions of years, but by nearly a full right angle. By 98 degrees, to the point where the poles of Uranus now point almost directly toward the Sun rather than perpendicular to its orbit. That collision happened once, it cannot be undone, and the sideways roll it produced has shaped everything about Uranus, its seasons, its magnetic field, its atmospheric dynamics, its relationship with its rings and moons for the 4.5 billion years since. To feel the full weight of what this collision represents, consider the geometry of the solar system before it happened. When planets form from a rotating protoplanetary disk, they inherit the angular momentum of that disk. The disk rotates in a specific plane, the plane of the ecliptic, and the planets that form within it tend to rotate in the same sense, their axes pointing roughly perpendicular to that plane. Not perfectly perpendicular, collisions and gravitational interactions during formation introduce small tilts, but broadly aligned. Earth tilts at 23.5 degrees, Mars at 25 degrees, Saturn at 27 degrees. These tilts are real and consequential, producing the seasons we experience and the varied climate patterns of the other planets. But these tilts are small, they are departures from the baseline, not violations of it. Uranus's 98-degree tilt is not a departure from the baseline, it is an overthrow of it, a tilt so extreme that the planet's rotational axis lies almost in the plane of its orbit rather than perpendicular to it. A tilt that makes Uranus look, when you examine its orbit in 3 dimensions, as though it is simply rolling along the plane of the solar system, like a marble rolling across a table. Something extraordinary produced this. The leading hypothesis, supported by the majority of planetary scientists who have studied the question, is a giant impact. Early in the solar system's history, when the planetary formation process was still underway, and the region of the outer solar system was populated by objects ranging in size from small planetesimals to protoplanets approaching Earth's mass, the orbital environment was chaotic in ways that have no modern equivalent. Resonances between the growing giant planets scattered smaller bodies into crossing orbits. Gravitational interactions sent objects on trajectories that the quiet solar system of today rarely produces. In this environment, the probability that a large body, something with a mass perhaps 1 to 3 times Earth's, substantial enough to qualify as a protoplanet in its own right, could be placed on a collision course with the young Uranus was not negligible. It was, in the context of the chaotic early solar system, a plausible consequence of the gravitational dynamics operating at the time. The collision, when models reconstruct it, would not have been instantaneous in any human sense, but at geological scales, it was extraordinarily rapid. A body of roughly Earth's mass, traveling at tens of kilometers per second relative to Uranus, striking the young ice giant at an angle calculated to maximize the transfer of angular momentum to the planet's rotation, rather than simply adding mass to its bulk. The angle matters enormously. A direct head-on collision would have imparted momentum primarily to Uranus's orbital velocity, speeding it up or slowing it down, potentially changing its orbit. A glancing impact, striking at an oblique angle, transfers momentum primarily as rotational angular momentum, spinning the planet, tilting its axis, altering its rotation in ways that a direct hit would not. The impact that tilted Uranus appears to have been precisely this kind of glancing blow. Not a head-on collision that might have disrupted the planet entirely, but a grazing impact that struck with enough angular momentum to permanently alter the planet's rotation axis while leaving the bulk of the planet intact. Computer simulations of this impact have been run many times by multiple research groups, with increasing sophistication as computational power has grown. The results are broadly consistent. An impactor of approximately 1 to 3 Earth masses, striking at an oblique angle, can produce a tilt in the resulting planet broadly consistent with Uranus's observed 98 degrees. But the simulations also reveal a complication that a simple impact scenario does not immediately explain. Uranus's moon's orbit in the plane of Uranus's equator tilted along with the planet, sharing the 98-degree tilt of the planet's own rotation. This is expected for moons that formed from a disk of debris around Uranus after its formation. If the impact tilted Uranus, the moons that subsequently formed from post-impact debris would naturally orbit in the tilted equatorial plane. But there are constraints on when the impact occurred. If it happened very early in solar system history, while the protoplanetary disk was still present, the disk's gravitational influence might have retilted Uranus back toward vertical before the final configuration was established. If it happened too late, after the disk had dispersed, there would be no mechanism to explain certain features of the moon system. Recent simulations, published within the last decade, using more sophisticated models of how an impactor's material interacts with an ice giant's interior, suggest that the impact may have been not one event, but possibly two. A first impact tilting Uranus significantly, followed by a second impact that set the final orientation. Or alternatively, a single large impact whose specific dynamics, when modeled at sufficient resolution, can reproduce both the tilt and the moon system configuration simultaneously. The question is not fully resolved. The giant impact hypothesis is the consensus explanation for Uranus's tilt. The specific details of that impact, its exact size, timing, angle, and whether it was a single event or multiple collisions, remain areas of active research. The impact left other signatures beyond the tilt itself, subtle markers of a violent history that careful analysis of Uranus's current properties reveals. One of the most significant concerns the planet's internal heat, or rather, its remarkable lack of it. Every other giant planet in the solar system radiates significantly more energy into space than it receives from the sun. Jupiter emits approximately 1.7 times as much energy as it receives. Saturn emits approximately 1.8 times as much. Neptune, despite being the farthest of the four giant planets from the sun, emits approximately 2.6 times as much energy as it receives, radiating heat from its interior in quantities that drive active atmospheric dynamics and produce weather systems visible from Earth. Uranus emits almost no internal heat. Its measured heat flux from the interior is so low, essentially consistent with zero, within the measurement uncertainties, that Uranus appears to be in thermal equilibrium with the solar radiation it receives, radiating away approximately what it takes in and nothing more. Why does Uranus retain so little internal heat? Several hypotheses have been proposed, and the giant impact may be relevant to the answer. If the impact created a thermal barrier in Uranus's interior, a layer of material whose composition or density structure prevents the heat of the deep interior from conducting outward efficiently, then the internal heat generated during formation and subsequent contraction could be effectively trapped, unable to escape to the surface, and unable to drive the vigorous convection that keeps Neptune's interior actively releasing heat. The impact may have sealed Uranus's warmth inside it. The planet may be carrying the heat of its formation still, locked in its interior by the layered structure that the collision created, a planet sitting on a store of energy it cannot release, cold on the outside and potentially hot on the inside. There is one more consequence of the tilting impact that shapes Uranus in ways that are not immediately obvious from the tilt alone. The impact almost certainly affected the young planet's rotation rate. Before the collision, Uranus was likely rotating at a rate broadly similar to what Jupiter and Saturn rotate at today, completing a full rotation in perhaps 10 to 12 hours. The impact's angular momentum added to or subtracted from this rotation, resulting in Uranus's current rotation period of approximately 17 hours and 14 minutes. But more significantly, the impact set the direction of rotation. Uranus rotates in the retrograde sense, clockwise when viewed from above the solar system's north pole, opposite to the direction of its orbital motion, and opposite to the rotation direction of most other planets. The 98-degree tilt combined with the retrograde rotation means that Uranus is technically tilted slightly past the point of inversion, so that what would conventionally be called its north pole is actually pointing southward, below the plane of the ecliptic. A planet whose north pole points south, rolling sideways through space, its moons tilted along with it, its seasons defined by 42-year periods of continuous polar sunlight and darkness, its internal heat trapped by a layer created in the violence of an ancient collision. All of this, the entire character of the strangest planet in the solar system, traces back to a single event that lasted perhaps hours in geological terms. A collision so long ago that the impacting body left no surviving fragments we can identify, recorded only in the orientation of a world still rolling on its side billions of years later. What that tilted orientation actually means for the planet's seasons, for the extraordinary, almost incomprehensible experience of time and light on a world whose poles spend decades in continuous sunlight and decades in continuous darkness, is a story that deserves its own careful telling. Because the seasons of Uranus are unlike anything that exists anywhere else in the solar system, and understanding them requires setting aside every intuition built from a lifetime of experiencing seasons on a world whose tilt is a gentle, manageable 23.5 degrees. Uranus's seasons require a different kind of imagination entirely. Seasons on Earth are something you feel in your body. The gradual lengthening of days in spring, the particular quality of summer light in the early evening, warm and golden and lasting far longer than it has any right to. The smell of autumn in the air weeks before the leaves change, some combination of cooling soil and drying vegetation that the body recognizes before the mind has consciously registered the shift. The compressed, dark, interior quality of winter days when the sun barely clears the horizon, and the light that arrives is thin and pale and seems to carry no warmth at all. These rhythms are so deeply embedded in human experience that they have shaped language, mythology, agriculture, architecture, religion, and the fundamental structure of how human civilizations organize time. Every culture that has ever existed in a location with discernible seasons has built those seasons into the fabric of its understanding of the world. Seasons feel ancient, fundamental, like a basic property of existence rather than a consequence of the specific tilt angle of the particular planet we happen to inhabit. But seasons are not fundamental, they are geometrical. They are what happens when a tilted planet orbits a star, when one hemisphere leans toward the star during part of the orbit and away from it during another. Change the tilt and you change the seasons. Change the tilt dramatically enough and you get something that the word season barely covers. Change it to 98 degrees and you get Uranus. A full orbit of Uranus around the Sun takes approximately 84 Earth years. This single number, combined with the 98-degree axial tilt established by the ancient collision, produces the most extreme seasonal cycle of any planet in the solar system. Not extreme in the sense of large temperature differences, we will explore Uranus's temperature environment in the next section of our journey. Extreme in the sense of duration, of the sheer length of time each part of the planet spends in sunlight and in darkness. Consider what the 98-degree tilt means for Uranus's poles during the course of an 84-year orbit. When Uranus's north pole is tilted toward the Sun, during what would conventionally be called its northern summer, that pole receives continuous sunlight, not the prolonged summer days of Earth's Arctic regions, where the midnight sun is a seasonal curiosity lasting a few weeks. Continuous sunlight, 24 hours a day, for an extended period measured not in weeks or months but in years. Approximately 21 years of continuous polar daylight, as the planet moves through the portion of its orbit where the tilted pole remains in the sun's illumination. During this same period, the opposite pole, the south pole, is pointed away from the sun. It receives no sunlight, not reduced sunlight, not the weak illumination of a polar winter. No sunlight at all, for approximately 21 years of continuous polar darkness. Then, as Uranus continues its orbit and the geometry shifts, the poles pass through an equinox, a period when the sun illuminates the equator more directly, and both poles receive more equal illumination. These equinox periods are the closest Uranus comes to the kind of seasonal balance Earth experiences continuously. And then the cycle reverses. The opposite pole tilts toward the sun. The 21-year period of illumination and darkness shifts hemispheres. The mathematics of this seasonal cycle, produces consequences for Uranus's atmosphere and energy distribution that planetary scientists are still working to fully understand. On Earth, the equatorial regions are perpetually the warmest parts of the planet. They receive the most direct solar illumination throughout the year, and seasonal variations at the equator are modest compared to the dramatic swings experienced at higher latitudes. The poles are coldest because they receive the least direct sunlight, averaged over the year. On Uranus, this relationship is inverted during solstice periods. When a pole is facing the sun, it receives more total solar energy over a Uranian year than the equator does, the 21 years of continuous sunlight delivering more cumulative energy than the equatorial regions receive during the same period. The poles, during their sunlit seasons, should theoretically be the warmest part of Uranus. Whether this is actually the case, whether Uranus's atmosphere responds to its extraordinary seasonal forcing in the way simple models would predict, turns out to be a genuinely complicated question. Uranus's nearly complete lack of internal heat means that the atmospheric dynamics are driven almost entirely by the external solar forcing, rather than by the kind of internal convection that shapes the weather of Jupiter and Neptune. This makes Uranus's atmosphere peculiarly sensitive to its solar environment in ways that the other giant planets are not. When Voyager 2 flew past Uranus in 1986, the spacecraft encountered the planet near its southern summer solstice, the period when the South Pole was tilted most directly toward the sun. And yet the temperature measurements Voyager 2 returned showed something unexpected. The equatorial regions of Uranus were not dramatically colder than the pole despite receiving less direct sunlight. The atmosphere appeared to be distributing heat laterally with a thoroughness that simple geometric models would not have predicted. How Uranus moves heat around its interior and between its hemispheres, given its unusual energy budget and its extreme tilt, is one of the planet's most actively investigated atmospheric puzzles. The equinoxes of Uranus deserve particular attention because they are the moments when the planet's strangeness becomes most dynamically visible. Uranus reached an equinox in 2007, the most recent one, observed with the best telescopes available at the time. In the years surrounding that equinox, as the geometry shifted and the illumination pattern across the planet changed, Uranus's atmosphere did something it had not done during the Voyager 2 flyby 2 decades earlier. It became active. Where Voyager 2 had found a planet of almost unsettling calm, a smooth, nearly featureless blue-green disk with none of the swirling storms and cloud bands that characterize Jupiter and Saturn, ground-based and space-based observations in the years around the 2007 equinox revealed atmospheric dynamics of considerable energy. Bright cloud features appeared, storm systems developed, the banding structure of the atmosphere became more pronounced. Uranus, apparently roused from its solstice period calm by the changing illumination of the equinox, showed its atmosphere was capable of significant activity. This equinox-driven awakening has led scientists to revise their understanding of Uranus's atmospheric dynamics. The placid appearance Voyager 2 encountered was not necessarily Uranus's default state. It may have been a consequence of the specific seasonal phase during which the only spacecraft visit occurred. Uranus near its equinox may be a significantly more dynamic world than the bland blue ball the Voyager images suggested. The next Uranian equinox will occur in approximately 2049. Whatever spacecraft humanity has managed to send to Uranus by that time, and there are current proposals for an orbiter mission that could arrive in the late 2030s or early 2040s, would observe a planet in one of its most active phases. There is a specific feature of the Uranian day that emerges from the 98-degree tilt and deserves its own moment of careful consideration. At the equator of Uranus, during the solstice periods when a pole is directed toward the sun does not rise and set in the way it does anywhere on Earth. Instead, it traces a path in the sky that is specific to a world tilted almost on its side. During a Uranian equinox, the periods of most Earth-like geometry, an observer at the equator would see the sun rising roughly in the east, arcing across the sky, and setting in the west in a pattern not entirely unlike an Earth sunrise and sunset. The day would be approximately 17 hours long, Uranus's rotation period. which, while shorter than an Earth day in absolute terms, would be recognizable as a day in the conventional sense. But during the solstice periods, the experience is profoundly different. At the pole directly facing the sun sits almost directly overhead and barely moves across the sky as Uranus rotates, a near-stationary blazing presence, providing continuous illumination without anything that could be called a sunrise or a sunset for years on end. At the equator during solstice, the geometry produces a sun that rises and sets every 17 hours, but rises and sets almost directly over the same point on the horizon, tracing a small circle in the sky rather than a sweeping arc from east to west. The sun moves, but it moves strangely, circling back toward the same horizon it rose over, like a light on a slow pendulum, rather than crossing the sky. No human being has ever experienced a day like this. No instrument has ever measured one from the surface. Uranus has no solid surface in any meaningful sense, and no probe has survived in its atmosphere long enough to record one. The Uranian day, with all its geometric strangeness, exists currently only in the mathematics of orbital mechanics and atmospheric physics. 84 years for one orbit, 21 years of polar daylight followed by 21 years of polar night. Equinoxes that rouse the atmosphere from solstice period calm. A day of 17 hours experienced in a geometry so tilted that the very concept of sunrise requires rethinking. The seasons of Uranus are not simply the seasons of Earth scaled up or made more extreme. They are qualitatively different, a different relationship between a planet and its star, a different organization of time and light and heat, produced by a tilt so large that the intuitions built from living on a gently tilted world do not transfer. And those extraordinary seasons, that unusual relationship with sunlight, that 84-year orbit through such different illumination conditions, act on an atmosphere whose appearance is, at first glance, almost deceptively simple. A smooth, pale, blue-green ball, featureless from a distance, calm in a way that the other giant planets are not. But that calm conceals a complexity that goes far deeper than the surface color suggests, because the atmosphere of Uranus, the thing that gives it its distinctive appearance, the thing that Voyager 2 photographed and found so surprisingly blank, is doing something that requires careful chemistry and careful physics to understand. In understanding it starts with a molecule that, on Earth, we associate with the flames of a kitchen stove and the distinctive odor of a gas leak. A molecule so simple it consists of just one carbon atom and 4 hydrogen atoms. Methane. Color carries information. Not just aesthetic information, not just the kind of information that tells you whether a sunset is beautiful or a painting is pleasing. Physical information, chemical information. The color of a planet, measured carefully across multiple wavelengths of light and analyzed with the right instruments, is a direct record of what that planet's atmosphere contains, how it is structured, and how it interacts with the sunlight passing through it. The color of Earth seen from space tells you there is liquid water on its surface and oxygen in its atmosphere. The reddish hue of Mars tells you its surface is rich in iron oxide. The brilliant white of Venus tells you its cloud deck is composed of highly reflective particles. Every planetary color is a message, written in the physics of light and matter, waiting to be read by instruments sensitive enough to decode it. The color of Uranus is blue-green, a particular shade, pale, soft, almost pastel, that planetary scientists describe as cyan, not the deep, saturated blue of Earth's oceans seen from space, not the vivid azure of Neptune, which shares Uranus's basic atmospheric chemistry but appears a noticeably deeper, richer blue, something more muted, more ambiguous, a color that sits at the boundary between blue and green and resists easy categorization. That color is a message, and the message it carries is about a molecule whose presence in Uranus's atmosphere does something that no other substance in that atmosphere does. It removes light from the spectrum before it can be reflected back to the observer, creating an absence that registers, to any eye looking at the planet from afar, as color. Methane is colorless in everyday experience. The gas that burns in kitchen stoves, that heats homes, that powers industrial processes, in the quantities and at the pressures where humans encounter it on Earth, methane is transparent, invisible. It does not absorb visible light in any way that would make it appear colored to the human eye. But Uranus's atmosphere is deep, enormously, almost incomprehensibly deep, a column of gas extending thousands of kilometers from the cloud tops to the regions where pressure becomes so great that the distinction between gas and liquid loses meaning. And in a column of gas that deep, even a weak absorber of light becomes significant. Light passing downward through thousands of kilometers of methane-containing atmosphere, reflecting off clouds below, and then passing upward through the same column again, has traveled through enough methane that even its weak absorption has had time to act. What methane absorbs specifically is red light. The longer wavelengths of visible light, the reds and oranges that make up the warm end of the visible spectrum, are selectively absorbed by methane molecules as sunlight passes through the deep Uranian atmosphere. By the time the light has made the round trip through that atmosphere and returned to space, the red wavelengths have been removed, depleted. What remains is the shorter wavelength light, the blues and greens, reflected back to any observer watching from afar. The blue-green color of Uranus is the color of sunlight with its red wavelengths eaten away by methane. It is the visual signature of a molecule present in small but significant quantities, approximately 2.3% of Uranus's atmosphere by volume, acting on light over a path length so enormous that its otherwise negligible absorption becomes the defining visual characteristic of an entire planet. Here is where something genuinely puzzling enters the picture. Neptune's atmosphere contains methane in concentrations broadly similar to Uranus's, approximately 1.5% by volume, somewhat less than Uranus but in the same general range. The same methane absorption physics should apply to both planets. The same removal of red wavelengths, the same enhancement of blue-green reflected light, the same mechanism operating in both atmospheres. And yet Neptune is visibly, measurably, distinctly bluer than Uranus. Side by side, the difference is immediately apparent. Uranus is pale, a muted, washed-out blue-green that almost seems reluctant. Neptune is vivid, a deep, rich, saturated blue that has a presence Uranus lacks. The same basic chemistry, producing noticeably different colors. Why? The answer, it turns out, is not fully understood, and this is one of those scientific situations where the admission of uncertainty is more honest and more interesting than any confident explanation would be. Recent analysis, published in 2022 by a team using spectroscopic data from multiple telescopes, has proposed a partial explanation involving the specific structure of the cloud systems in each planet's atmosphere. Both Uranus and Neptune appear to have a layer of haze particles high in their atmospheres, a photochemical smog of sorts, produced when ultraviolet radiation from the sun breaks down methane and other molecules in the upper atmosphere, producing complex organic compounds that condense into tiny particles and form a haze layer. On both planets, this haze layer affects the color of the light reflected from the atmosphere. On Neptune, the haze layer appears to be thinner than on Uranus, possibly because Neptune's more vigorous internal heat drives stronger atmospheric circulation that mixes the haze particles downward more efficiently, reducing the thickness of the haze layer aloft. On Uranus, with its near-total lack of internal heat and its more sluggish atmospheric circulation, the haze particles accumulate in a thicker layer. This thicker haze on Uranus acts as an additional reflector of light, bouncing back some of the incoming sunlight before it has had a chance to penetrate deeply enough for methane absorption to remove the red wavelengths effectively. The result is a paler, more washed-out appearance. The methane absorption is partially counteracted by the additional reflection from the haze layer, reducing the saturation of the blue-green color. The difference in color between Uranus and Neptune, that obvious visual distinction between the pale ice giant and the vivid one, may come down to the difference in their haze layers, driven ultimately by the difference in their internal heat outputs. Uranus's missing heat, whose absence we will explore in depth in the next section of our journey, may be directly responsible for the paler shade of blue that distinguishes it from its outer neighbor. Below the haze layer, the atmospheric structure of Uranus descends through a sequence of layers that planetary scientists have been mapping with increasing precision using a combination of spacecraft data, ground-based telescopic observations, and theoretical modeling. The uppermost region of Uranus's atmosphere is the stratosphere, a relatively warm layer where the absorption of solar ultraviolet radiation heats the gas above the temperatures of the cloud layers below. Here, the photochemical reactions that break down methane produce complex organic molecules, acetylene, ethane, and other hydrocarbons that have been detected spectroscopically in the infrared emission of the planet. These molecules accumulate in the stratosphere and contribute to the haze that gives Uranus its pale color. Below the stratosphere lies the troposphere, the region where the bulk of the visible weather occurs, where temperatures decrease with altitude until they reach their minimum at the tropopause, then begin to increase again with depth as pressure increases. The minimum temperature in Uranus's troposphere is approximately -224 degrees Celsius, the coldest atmospheric temperature of any planet in the solar system, a fact we will examine carefully in the next section. Within the troposphere, 3 distinct cloud layers have been identified from models and partially confirmed by observations. The uppermost is a methane ice cloud layer. Methane, under the temperatures and pressures of the upper troposphere, condenses into ice crystals that form a thin cloud deck. Below this is a hydrogen sulfide cloud layer, a compound of hydrogen and sulfur that condenses at somewhat greater depths where temperatures are warmer. And below that, deeper still, is an ammonia and water cloud layer, sitting at pressures where the atmosphere is warm enough that liquid droplets may be present alongside ice crystals. These cloud layers are not as visually dramatic as the banded cloud systems of Jupiter or the complex storm features of Saturn. In most observations, the cloud deck of Uranus appears remarkably uniform, the deep cloud layers hidden behind the haze above, contributing to the smooth, nearly featureless appearance that struck Voyager 2's cameras in 1986. But the clouds of Uranus are not entirely absent of features, and the features that do appear reveal something about the atmospheric dynamics that the smooth overall appearance disguises. In the years around the 2007 equinox, as noted in our previous section, bright cloud features became visible in Uranus's atmosphere at levels and in frequencies not seen during the Voyager epoch. Some of these features were identified as discrete storm systems, convective clouds driven upward through the atmosphere by the same kind of buoyancy-driven convection that creates cumulus clouds on Earth, but operating in an atmosphere of hydrogen and helium rather than nitrogen and oxygen. The brightest of these storm features have been tracked as they move through the atmosphere, their drift velocities providing information about the wind speeds at different latitudes. The wind pattern on Uranus shows a retrograde jet at the equator, winds moving in the opposite direction to the planet's rotation, and prograde jets at higher latitudes, producing a banded wind structure, broadly similar to what is found on Jupiter and Saturn, though far less visually obvious in Uranus's case, because the cloud features that make the banding visible on the other planets are largely absent on Uranus. The winds of Uranus reach speeds of approximately 900 kilometers per hour at some latitudes, comparable to the wind speeds on Neptune, and significantly faster than the most powerful winds ever recorded on Earth. The atmosphere of this apparently calm planet is, in fact, moving at extraordinary velocities that only become apparent through careful tracking of cloud features over time. The color of Uranus is pale blue-green, the color of methane's appetite for red light, modified by a thick haze of photochemical particles and filtered through a deep, layered atmospheric structure. The color of a world whose atmosphere is simultaneously chemically complex and visually restrained, concealing its real dynamics behind a surface of apparent simplicity. But the color is only the outermost layer of what Uranus is showing us. Beneath the blue-green haze, beneath the cloud layers of methane and hydrogen sulfide and ammonia, beneath the troposphere where the visible weather occurs, the atmosphere of Uranus continues downward, thickening, warming, pressurizing, into regions where the very concept of an atmosphere begins to give way to something else entirely. Something that, at the temperatures and pressures reached in Uranus's deep interior, requires a different vocabulary, not gas, not liquid, not solid, but exotic states of matter that have no everyday analog, states that may be responsible for some of the most counterintuitive properties of this extraordinary planet. And the most counterintuitive property of all, the one that sets Uranus apart from every other giant planet and has resisted explanation for decades, is the near-total absence of heat flowing outward from its interior. A planet 14 times Earth's mass, formed from the heat of collisions and accretion, ancient beyond comprehension. And cold. Heat is patient. It does not disappear. It does not simply stop existing because the process that generated it has ended. Heat is a form of energy, and energy in the accounting that physics requires is never created or destroyed, only transferred, converted, moved from one place to another or from one form to another, but never simply gone. When a planet forms, when billions of collisions between planetesimals and larger bodies accumulate mass and release kinetic energy as heat over tens of millions of years, that heat is deposited into the interior of the growing world. It does not vanish when the collisions stop. It remains stored in the rock and ice and metal of the planet's interior, slowly radiating outward through whatever mechanisms the planet's structure permits: conduction through solid layers, convection through fluid ones, the patient, continuous flow of thermal energy from hot interior to cold space. For the giant planets of the outer solar system, this residual heat of formation is not a minor phenomenon. It is a dominant feature of their energy budgets. Jupiter radiates approximately 1.7 times more energy into space than it receives from the Sun, the excess representing the steady outward flow of heat deposited during its formation billions of years ago. Saturn does the same, and Saturn's internal heat source is supplemented by an additional process: the precipitation of helium droplets through the liquid hydrogen interior, releasing gravitational potential energy as the denser helium settles toward the core. Neptune, despite being the most distant of the four giant planets and receiving less solar energy per square meter than any of them, emits approximately 2.6 times as much energy as it receives, its interior vigorously convecting, its internal heat driving the active atmospheric dynamics that produce Neptune's visible storms and cloud features. And then there is Uranus. Uranus emits essentially no detectable internal heat. Not reduced internal heat, not a modest internal heat flux smaller than Neptune's, essentially none. The measurements of Uranus's total energy output, made by Voyager 2 and subsequently refined by ground-based and space-based observations, show that the planet radiates approximately the same amount of energy into space as it receives from the Sun. Within the measurement uncertainties, the internal heat contribution is consistent with zero. For a planet of Uranus's size and age, this is profoundly anomalous. The heat of formation alone should be radiating outward at a measurable rate for billions of years. The gravitational compression of the interior, as the planet contracts under its own weight, should be releasing additional energy. The decay of any radioactive elements incorporated into the rocky core should contribute a thermal signature. All of these heat sources should be present. All of them should be producing a measurable outward heat flux. They are not, or rather, whatever heat they are producing is not reaching the surface and being radiated into space. Where is the heat? The answer most favored by current models is neither obvious nor simple, and it connects directly to the giant impact we explored in our third section through mechanisms whose details are still being worked out. When a large impactor struck the young Uranus and permanently altered its rotation axis, it did not merely tilt the planet. It disrupted the planet's interior structure. The energy of the collision, enormous, deposited rapidly into the outer layers of the ice giant, created a complex layering in the planet's interior that may have fundamentally altered how heat flows outward from the core. Under normal circumstances, the interior of a giant planet is convectively unstable. The hot interior rises, the cooler material above sinks, and the resulting convection carries heat efficiently from depth to the surface. This is what drives the internal heat flux of Jupiter, Saturn, and Neptune. Convection is efficient. Given a hot interior and a convectively unstable stratification, a giant planet will radiate its internal heat outward at a rate limited primarily by how quickly heat can be transported through the outer layers to space. But if some layer within the planet is compositionally stable, if there is a region where denser material underlies less dense material in a stratification that suppresses convective overturning, then that layer acts as a thermal blanket. Heat from below cannot pass through by convection. It can only be conducted slowly through the stable layer, at a rate far lower than convection would permit. The giant impact may have created exactly such a stable layer in Uranus's interior. The collision mixed different compositional layers in a way that produced a stratification capable of suppressing convection. Heat generated in the deep interior cannot efficiently cross this barrier. It accumulates below the stable layer. The planet's interior may actually be warm, perhaps significantly warmer than a naive estimate of Uranus's thermal evolution would suggest, but that warmth cannot escape. Uranus is not a cold planet that has lost its heat. It may be a planet whose heat is imprisoned. Testing this hypothesis observationally is extraordinarily difficult because we cannot directly measure the temperature of Uranus's deep interior. What we can measure, and what provides important indirect constraints on the interior thermal structure, is the temperature of the observable atmosphere, the gravitational field of the planet, and the behavior of the magnetic field. All three provide clues, and all three point toward an interior that is more complex and more thermally stratified than the interiors of Jupiter and Saturn. The temperature structure of Uranus's upper atmosphere shows a stratification that differs subtly but measurably from the temperature profiles of the other giant planets. The rate at which temperature increases with depth in the troposphere, the lapse rate in meteorological terminology, is affected by the presence of different condensable species at different altitudes. The specific lapse rate profile of Uranus's atmosphere is consistent with significant compositional layering in the deeper atmosphere, potentially extending the thermal barrier effect from the deep interior into the atmospheric layers more accessible to observation. The gravitational field of Uranus, measured by tracking the precise motion of Voyager 2 during its flyby, and by subsequent ground-based observations of how Uranus's gravity influences the orbits of its moons, constrains the density distribution within the planet. Different interior models predict different gravitational field structures, and the observed gravity provides constraints on which models are physically plausible. These constraints are consistent with significant density stratification in the interior, a picture of compositional layering rather than the more uniform interiors of Jupiter and Saturn. There is a comparison that illuminates the anomaly of Uranus's missing heat more sharply than any abstract description. Neptune. Neptune and Uranus are often treated as a pair, sister worlds, similarly sized, similarly composed, both ice giants orbiting in the outer solar system. Their masses are similar. Neptune is approximately 17 times Earth's mass, Uranus approximately 14 times. Their radii are similar. Their atmospheric compositions are broadly comparable. Their distances from the Sun differ by less than a factor of 2. And yet Neptune emits 2.6 times as much energy as it receives from the Sun, while Uranus emits essentially nothing beyond what it receives. This difference, so large between two planets that are in so many respects similar, demands explanation. Some proposed explanations focus on the differences in their histories. Perhaps Neptune did not experience the same kind of tilting impact that Uranus experienced, and therefore does not have the same thermally insulating compositional layers in its interior. Perhaps the specific size, angle, and composition of the impactor that struck Uranus were unique in producing a particularly effective thermal barrier. Perhaps Uranus's slightly smaller mass means its interior pressures and temperatures fall in a range where certain compositional stratifications are thermodynamically stable in a way they are not in Neptune's slightly more massive interior. None of these explanations has been definitively confirmed. The comparison between Uranus and Neptune, why two worlds so similar are so different in their thermal behavior, remains one of the most compelling open questions in ice giant science. The coldest temperatures in Uranus's atmosphere occur not at the top of the atmosphere, where the planet is most exposed to the cold of space, but at a specific altitude within the troposphere, a layer called the tropopause, where the temperature reaches its minimum before beginning to rise again with increasing depth. At Uranus's tropopause, the temperature reaches approximately -224 degrees Celsius. This is 49 degrees Celsius above absolute zero, astonishingly cold by any standard, and the coldest measured atmospheric temperature of any planet in the solar system. Not the coldest surface temperature, the permanently shadowed polar craters of Mercury reach temperatures of approximately -200 degrees Celsius, and certain locations in the outer solar system on icy bodies are colder still, but the coldest atmospheric temperature of any planet. The reason the minimum temperature occurs at the tropopause rather than the top of the atmosphere involves the energy balance at different altitudes. In the stratosphere above the tropopause, solar ultraviolet radiation warms the gas directly. In the troposphere below, the increasing pressure and the residual heat from the interior, minimal as it is, warm the atmosphere with depth. The tropopause is the altitude where both of these warming influences are at their minimum, above the depth where pressure-driven warming becomes significant, and below the altitude where solar ultraviolet heating is most effective. -224 degrees Celsius, a temperature at which most gases encountered in everyday experience would not merely freeze, but would solidify at pressures barely distinguishable from vacuum. A temperature cold enough that hydrogen, the dominant component of Uranus's atmosphere, begins to show quantum mechanical effects in its behavior that are essentially absent at terrestrial temperatures. The coldness of Uranus's observable atmosphere and the imprisonment of its interior heat are not simply curiosities, interesting anomalies to be noted and set aside. They shape the planet's atmospheric dynamics in ways that make Uranus fundamentally different from the other giant planets in its behavior, its appearance, and the nature of the weather systems it produces. A planet with no internal heat source driving convection from below is a planet whose atmospheric dynamics are almost entirely controlled from above, by the solar energy arriving at the top of the atmosphere, absorbed at various altitudes, and driving the circulation patterns that redistribute heat laterally across the planet. This is a fundamentally different regime of atmospheric dynamics from what operates on Jupiter and Neptune, where vigorous internal convection drives weather from below and maintains the active storm systems and banded structures those planets display. Uranus's atmosphere operates, in a sense, upside down compared to the other giant planets, driven from the top rather than from the bottom, organized by external forcing rather than internal convection. This unusual energetic configuration is part of why Uranus appeared so bland and featureless to Voyager 2 during its brief encounter. The atmospheric dynamics simply work differently when the engine is not running. But the engine is not entirely absent. The solar forcing, limited as it is at Uranus's distance from the Sun, does drive circulation. The seasonal changes in solar illumination, operating over the 84-year orbital period, do force atmospheric responses. And when those seasonal forcings are strongest, near the equinoxes, the atmosphere responds with storm systems and cloud features that the Voyager images, taken near southern solstice, could not have revealed. Uranus's atmosphere is quiet, not dead. And deep below that quiet atmosphere, below the cold tropopause and the cloud layers and the haze and the methane and the hydrogen and the everything that makes up what we conventionally think of as a planet's atmosphere, something extraordinary begins. The transition from atmosphere to interior on Uranus is not a sharp boundary. There is no surface to cross. The gas simply gets denser and hotter and more pressurized with increasing depth until, at some point, it has become so dense that the distinction between gas and liquid no longer applies in any meaningful sense. And in that dense, pressurized, hot interior, hidden from any observation more direct than the gravitational and magnetic field measurements that constrain it indirectly, some of the most remarkable physical processes in the solar system may be occurring. Processes that produce substances and phenomena that challenge every ordinary intuition about what the interior of a planet should contain. Among them, perhaps most extraordinarily, diamonds. Not metaphorical diamonds, not a comparison or an analogy. Actual diamonds, carbon crystallized under pressure into the hardest naturally occurring substance known, potentially forming in the interior of Uranus in quantities and under conditions that have no equivalent anywhere on Earth. Pressure does strange things to matter. Not strange in the colloquial sense, not strange the way an unusual weather pattern or an unexpected chemical reaction is strange. Strange in the deepest physical sense. Pressure applied with sufficient force to any substance fundamentally alters the relationships between atoms, compressing the space between them, forcing electrons into new configurations, reorganizing the structure of matter at the quantum mechanical level into arrangements that simply do not exist under ordinary conditions. On Earth, we encounter the effects of pressure in modest ways. Water compressed under the enormous pressures of the deep ocean remains liquid at temperatures well below its normal freezing point, the pressure shifting the phase boundary. Carbon, squeezed under the conditions found in the Earth's upper mantle, transforms from soft graphite into the rigid crystal lattice of diamond. Iron, under the pressure of the Earth's inner core, remains solid despite temperatures exceeding the surface of the Sun, the pressure preventing the thermal energy of the atoms from breaking the crystal structure apart. These Earth-scale examples are merely the beginning. The pressures inside Uranus reach values that make Earth's deep interior seem almost modest by comparison. Millions of atmospheres, tens of millions of atmospheres. Pressures so extreme that the behavior of matter under those conditions is accessible to experiment only through the most powerful laboratory tools ever built, diamond anvil cells that squeeze tiny samples between the faces of gemstone diamonds, laser shock experiments that create extreme pressures for nanoseconds, computational simulations that calculate the behavior of quantum mechanical systems under conditions no physical laboratory can yet sustain. What those experiments and simulations reveal about the likely state of matter deep inside Uranus is one of the most remarkable stories in planetary science. Descend into Uranus from the cloud tops. The atmosphere thickens around you. The temperature, which reached its minimum at the tropopause, begins rising again as depth and pressure increase. The methane cloud layer passes overhead, the hydrogen sulfide clouds, the ammonia and water clouds deeper still. The atmosphere becomes denser, not dramatically, not in any way that could be perceived as a sudden transition, but continuously and relentlessly as the weight of the gas above presses down on the gas below. At some depth, perhaps 5,000 to 8,000 kilometers below the cloud tops, the pressure has risen to millions of atmospheres and the temperature to thousands of degrees Celsius. The distinction between gas and liquid, already blurred for thousands of kilometers above this point, has become entirely meaningless. What surrounds you is not a gas or a liquid in any conventional sense, but a supercritical fluid, matter in a state where the properties of gas and liquid merge into something with no ordinary name. The composition of this fluid is primarily water, with significant amounts of ammonia and methane, the ices that gave Uranus its classification as an ice giant, now existing under conditions that make the word ice seem absurd. The water is not frozen. The ammonia is not liquid in any ordinary sense. They are compressed into a dense, hot, exotic fluid under pressures and temperatures that place them in regions of their phase diagrams that laboratory science has only recently begun to explore. This vast region, extending from the base of the observable atmosphere down through thousands of kilometers of depth, is sometimes called the water-ammonia ocean of Uranus, though ocean carries connotations of calm and liquidity that do not capture the reality. It is an ocean in the sense of being a vast enclosed body of fluid material. It is not an ocean in any sense that would feel recognizable. In this fluid, something happens to ammonia that has no analog in everyday chemistry. Under the pressures present in Uranus's interior mantle, ammonia, the molecule NH3, consisting of one nitrogen atom bonded to 3 hydrogen atoms, transitions into a state called superionic ammonia. The nitrogen atoms in superionic ammonia form a rigid crystal lattice, locked in place by the extreme pressure. But the hydrogen atoms, lighter, more mobile, are freed from their bonds to the nitrogen and flow through the crystal lattice like a liquid. They move freely, carrying electrical charge as they flow, making superionic ammonia an electrical conductor despite the presence of the rigid crystalline nitrogen framework. Superionic ammonia is simultaneously solid and liquid. The nitrogen lattice is solid. The hydrogen fluid is liquid. The two coexist in the same material, at the same temperature and pressure, creating a state of matter with no ordinary counterpart. This extraordinary state has been confirmed experimentally. In 2018, researchers at Lawrence Livermore National Laboratory used laser shock experiments to create the pressures and temperatures estimated to exist in Uranus's interior, and directly observed the superionic transition in water, a closely related phenomenon where oxygen atoms form the rigid lattice and hydrogen atoms flow freely through it. The experiments confirmed that superionic phases of water and ammonia are not theoretical predictions, but physical realities that occur under conditions plausibly present in Uranus's interior right now. If superionic water and ammonia are present in Uranus's interior, and the experimental evidence strongly suggests they are, then the planet's interior mantle is composed of a material unlike anything that exists naturally on Earth's surface or in Earth's accessible geological record. A material that is simultaneously a solid crystal and a conducting fluid carrying electrical charge through its hydrogen component while maintaining structural rigidity through its heavier atomic framework. The electrical conductivity of superionic materials in Uranus's interior has consequences that extend from the deep interior to the space surrounding the planet. Magnetic fields in planetary interiors are generated by the motion of electrically conducting fluids, the dynamo mechanism that produces Earth's magnetic field from the flow of liquid iron in the outer core, and that produces Jupiter's and Saturn's magnetic fields from the flow of liquid metallic hydrogen in their deep interiors. The specific character of a planet's magnetic field, its strength, its geometry, its stability over time, depends on the geometry and dynamics of the conducting fluid generating it. In Uranus, the conducting fluid is not liquid metallic hydrogen deep in the core, as in Jupiter and Saturn, but superionic water and ammonia distributed throughout the mantle, a conducting layer that extends across a much broader region of the planet's interior than the deep dynamo regions of the gas giants. This difference in the geometry of the conducting region may be directly responsible for one of Uranus's most distinctive and puzzling properties, which we will explore in depth in a later section. For now, the important point is that the superionic interior of Uranus is not merely a physical curiosity. It is the engine of the planet's magnetic activity, the generator that produces the unusual field wrapping the planet in a configuration that has no parallel among the other giant planets. Deeper still, below the superionic mantle, the pressure reaches values where something remarkable happens to the methane component of Uranus's interior. Methane under extreme pressure, the specific pressures and temperatures estimated to exist in Uranus's deep interior, somewhere between 1 and 6 million atmospheres, is not stable as a molecule. The carbon and hydrogen atoms that make up methane are forced apart by the extreme conditions, dissociating from their molecular bonds into individual atoms, or combining into new structures not found under ordinary conditions. The carbon atoms released by this dissociation of methane encounter a problem of geometry under extreme pressure. Carbon at high pressure tends to adopt one of two crystal structures, graphite, where carbon atoms form flat sheets loosely bound together, which is stable at lower pressures, or diamond, where each carbon atom bonds to four neighbors in a tetrahedral arrangement, which is stable at higher pressures. Under the pressures present in Uranus's deep interior, diamond is thermodynamically favored. Carbon atoms released by the dissociation of methane in the deep interior of Uranus may be crystallizing into diamond. Not instantaneously, not at the rate of a snap of the fingers, but on geological timescales, continuously and steadily, as the conditions in the deep interior slowly evolve. Diamond crystals forming under extreme pressure, then, because diamond is denser than the surrounding fluid, sinking through the interior toward the rocky core. Diamond rains. The phrase seems almost too poetic for a scientific hypothesis, but laboratory experiments have tested this idea directly. In 2017, researchers at SLAC National Accelerator Laboratory fired laser pulses at a plastic material, chosen to approximate the carbon and hydrogen content of Uranus's interior, and created shock pressures comparable to those in the planet's deep interior. Diamond nanocrystals formed in the experiment within nanoseconds. The physics that produces diamond rain is not speculative. It has been demonstrated in the laboratory under conditions designed to replicate what Uranus's interior experiences continuously. Whether the diamond rain occurs at the scale and rate that some models predict, with diamonds potentially reaching centimeter or even larger sizes before sinking to the core, depends on the specific temperature profile and compositional details of Uranus's interior, which are not yet known precisely enough to make confident quantitative predictions. But the basic phenomenon, carbon crystallizing as diamond under the pressures of Uranus's deep interior and sinking inward, is physically plausible and experimentally supported. At the very center of Uranus, beneath the superionic mantle and the diamond rain zone, there is almost certainly a rocky core. Not a molten, active core like Earth's iron interior, a core of silicate and possibly metallic material compressed to extraordinary density under the weight of everything above it. The pressure at Uranus's center is estimated at approximately 8 million atmospheres, high enough to compress rock into states whose properties are poorly characterized even by the most advanced high-pressure laboratory experiments. The mass of this core is estimated at several Earth masses, a rocky heart that is itself larger than many planets elsewhere in the solar system might be, but which constitutes only a small fraction of Uranus's total mass, buried under the vast mantle of exotic ices and the outer envelope of hydrogen and helium. This rocky core may or may not be generating significant heat from the decay of radioactive elements within it. The contribution of such radiogenic heat to Uranus's total energy budget is uncertain, but even if present, it is apparently insufficient to drive the kind of vigorous mantle convection that would carry heat efficiently to the surface. The thermal barrier in the interior, the compositional stratification potentially created by the ancient impact, continues to insulate the core's warmth from the outer layers, maintaining the cold exterior appearance of a planet that may be significantly warmer inside than its lack of outward heat flux suggests. Consider for a moment what Uranus actually is beneath its apparently simple blue-green exterior. A world whose interior contains matter in states that do not exist anywhere on Earth's surface. Superionic water that is simultaneously solid and liquid. Superionic ammonia conducting electricity through flowing hydrogen, while its nitrogen atoms sit rigid in a crystal lattice. Carbon crystallizing as diamond and raining inward through a hot, dense fluid. A rocky core compressed to densities that challenge laboratory science to reproduce and characterize. None of this is visible. None of it can be directly observed from the outside. It is inferred from the gravitational field, the magnetic field, the atmospheric composition, the results of laboratory experiments, and the calculations of theoretical physics applied to the conditions estimated to exist at various depths. Uranus is, in this sense, a planet whose true nature is hidden, not behind clouds, as Venus hides its surface, but behind the physics of extreme pressure and temperature that makes its interior inaccessible to any direct observation. And yet the interior communicates with the outside in ways that, if read carefully, reveal something of what lies within. One of those communications is the magnetic field, wrapped around Uranus in a configuration so bizarre that it defied every model of planetary magnetism that scientists had developed before Voyager 2 arrived and measured it directly. But before we follow the magnetic field outward from the interior, there is something else orbiting Uranus, something dark and thin and barely visible even to the best telescopes on Earth, whose existence was not even suspected until an astronomer was watching a star disappear behind the planet in 1977 and noticed something that should not have been there. Rings. On the night of March 10, 1977, an astronomer was not looking at Uranus. Not directly, not with the intention of studying the planet itself. James Elliott, along with colleagues aboard NASA's Kuiper Airborne Observatory, a modified C-141 cargo aircraft carrying a 91-centimeter telescope, flying at high altitude above the clouds and water vapor of Earth's lower atmosphere, was positioned to observe an event called a stellar occultation. A stellar occultation is among the most useful observational tools available to planetary astronomers. When a planet, moon, or other solar system body passes in front of a distant star as seen from Earth, the star's light is blocked, occulted, by the intervening object. By measuring precisely how the star's brightness changes as the body passes in front of it and then moves away, astronomers can deduce information about the body's size, shape, and atmospheric structure with a precision that direct imaging cannot match. The star acts as a point source of known brightness, and any deviation from the expected pattern of gradual dimming and brightening reveals something about the intervening object. On that March night, Uranus was predicted to pass in front of a faint star designated SAO 158,687. The occultation would last only about 25 minutes, during which Uranus's disk would cover the star entirely. But the observation window was much longer than the occultation itself, because the telescope needed to be tracking the star before and after the main event to establish the baseline brightness. It was during this baseline period, watching the star before Uranus's disk reached it, that Elliot noticed something unexpected. The star dimmed, briefly, in a pattern of multiple short dips in brightness, occurring in rapid succession, before recovering to its full brightness as if nothing had happened. And then, after the main occultation by Uranus's disk, the same pattern repeated, the same sequence of brief dips, in the same order on the other side. Something was orbiting Uranus, something that had passed in front of the star before the planet itself did, and passed in front of it again on the other side after the planet moved away. Multiple somethings, arranged in a system of rings that nobody had known was there. The discovery was immediately significant, but what made it particularly striking was not simply that Uranus had rings, it was the character of those rings. Saturn's rings, known and studied since Galileo first observed them in 1610, are brilliant. Composed primarily of water ice particles ranging in size from tiny grains to boulders meters across, they reflect sunlight with extraordinary efficiency, producing the most visually dramatic ring system in the solar system, visible even through a modest backyard telescope. When you look at Saturn through a telescope, the rings dominate the view. They are unavoidable, impossible to miss. Uranus's rings are the opposite. They are among the darkest objects in the solar system. The particles composing them reflect only a few % of the light that strikes them, comparable to coal or asphalt in their reflectivity, dramatically different from the brilliant ice of Saturn's rings. They are also narrow, extraordinarily narrow, compared to Saturn's broad, shimmering disk. The main rings of Uranus are typically only a few kilometers wide, some of them less, and they are dark enough that even with the knowledge of their existence, imaging them directly requires either the sensitivity of a spacecraft at close range or specialized techniques with the most powerful telescopes on Earth. This darkness and narrowness is why they went undetected for so long, not because they are small or unimportant, because they are almost completely black, arranged in thin dark lines orbiting a planet in the outer solar system, invisible in any ordinary photograph, revealed only by the indirect method of watching a star disappear behind them. Voyager 2's encounter with Uranus in January 1986 provided the first direct images of the ring system, and the images confirmed and extended what the occultation measurements had suggested. At the time of the Voyager 2 flyby, 9 distinct rings had been identified from Earth-based occultation observations. Voyager 2 confirmed these 9 and discovered 2 additional narrow rings, bringing the total to 11 in the main ring system. Subsequent observations from the Hubble Space Telescope and the Keck Observatory, benefiting from the improved clarity afforded by adaptive optics technology, identified 2 additional outer rings, dusty, diffuse, and different in character from the narrow main rings, bringing the total number of known rings to 13. The innermost ring is designated 1986 Utaur/Zeta, a broad, diffuse sheet of dust lying closest to the planet. The outermost of the main narrow rings, designated Epsilon, is the most prominent, wide enough to be detected with relative ease in occultation measurements, with a width that varies around its orbit from approximately 20 kilometers at its narrowest point to approximately 96 kilometers at its widest. This variation in the epsilon ring's width is itself scientifically significant. Rings, in the absence of forces acting to constrain them, tend to spread. Ring particles moving in slightly different orbits gradually disperse due to the small velocity differences between orbits at different distances from the planet. A narrow ring, left to itself, would broaden over geological time into a diffuse disk, rather than maintaining its sharp edges. Something is keeping Uranus's narrow rings narrow. Something is enforcing the sharp edges and preventing the dispersion that orbital mechanics would otherwise cause. The answer lies with small moons. Embedded within and alongside the ring system are a number of small satellites, moonlets too small to be easily detected in their own right, most of them discovered by Voyager 2 or subsequent observations, several of them orbiting in close proximity to specific rings. These moonlets act as what planetary scientists call shepherd moons, their gravitational influence herding the ring particles into the narrow lanes that produce the sharp-edged ring structure. The physics of shepherding involves a gravitational resonance between the ring particles and the shepherd moons. A moon orbiting just outside a ring moves more slowly than the ring particles, outer orbits being slower in the Keplerian mechanics of orbital dynamics. Ring particles that drift outward toward the shepherd moon's orbit exchange angular momentum with the moon through gravitational interaction, losing energy and dropping back into the ring's interior. Simultaneously, a moon orbiting just inside the ring moves faster than the ring particles and acts to push outward drifters back inward. The two shepherd moons essentially act as gravitational walls on either side of the ring, confining the ring particles to the narrow lane between their orbits. This mechanism was first clearly identified for Saturn's F-ring, but Uranus's rings provided additional examples of the process and helped establish it as a general feature of narrow planetary ring systems. The shepherd moons of Uranus's epsilon ring are Cordelia and Ophelia, named in keeping with the convention for Uranian moons from Shakespeare's works, specifically King Lear in Cordelia's case and Hamlet in Ophelia's. Small, dark, difficult to observe, they exert gravitational influence many times their visible size through the precision mechanics of orbital resonance. The composition of Uranus's ring particles is one of the outstanding uncertainties in ring science. The extreme darkness of the rings, their very low albedo, constrains the possible composition significantly. Water ice, which is bright and would produce the high albedo characteristic of Saturn's rings, is clearly not the dominant component. The most likely candidates for the dark ring material are complex organic compounds, carbon-rich molecules that absorb light efficiently, possibly mixed with silicate material or processed by radiation into dark, amorphous forms that bear little resemblance to their original chemical compositions. One hypothesis holds that the ring particles began as icy material, similar in composition to Uranus's icy moons, that was processed by the intense radiation environment of Uranus's magnetosphere over billions of years. Radiation bombardment of water ice and other icy compounds can produce dark, carbonaceous residues through a process called radiolysis, the breaking of chemical bonds by energetic particles and photons, and the subsequent reorganization of the fragments into complex organic structures. Over billions of years of exposure to the charged particles trapped in Uranus's magnetic field, originally bright icy ring material could be darkened into the coal-black particles observed today. This radiation processing hypothesis is plausible. It has been invoked to explain the dark surfaces of other icy bodies in the outer solar system, but it has not been confirmed by direct compositional measurement. The Voyager 2 flyby did not carry instruments capable of definitively characterizing the ring particle composition at the resolution needed to distinguish between different dark material hypotheses, and no subsequent mission has visited Uranus to provide more refined data. The two outermost rings, designated Mu and Nu, discovered by Hubble in 2003 and 2005, are fundamentally different in character from the narrow main rings and deserve mention as a separate phenomenon. These outer rings are broad and diffuse rather than narrow and sharp-edged. They are also, unusually for Uranian rings, not extremely dark. They appear to contain dust-sized particles that scatter light more efficiently than the larger particles of the main rings, giving them a slightly higher albedo, and they are blue. Blue rings. In the context of a ring system otherwise distinguished by its darkness and its difficulty of observation, the existence of blue rings orbiting Uranus is almost disorienting. Saturn's rings are white to tan. The main rings of Uranus are nearly black. The Mu ring is blue, actually blue, in a way measurable in the spectral data from Hubble's observations. The blue color of the Mu ring is thought to result from its composition, specifically from the presence of very fine dust particles in a specific size range where they scatter shorter wavelengths of light more efficiently than longer wavelengths, producing the blue color in reflected light. These fine dust particles are likely being continuously supplied by a small moon, MAB, discovered in the same Hubble observations that revealed the Mu ring, whose surface is being bombarded by micrometeorites that knock dust into the ring. MAB is embedded within the Mu ring, and the dust it supplies gives the ring its blue color and its diffuse structure. The relationship between MAB and the Mu ring is a miniature example of the same processes that maintain ring systems throughout the solar system: moons providing material, micrometeorite bombardment releasing it, and orbital dynamics distributing it into the ring structures we observe. The ring system of Uranus is not stable on geological timescales. The narrow rings lose material continuously, particles spiraling inward under the influence of atmospheric drag from the tenuous upper atmosphere that extends into the ring region, and through collisions that gradually erode the ring particles into smaller fragments that are more susceptible to drag. The shepherd moons that maintain the ring boundaries are themselves subject to orbital evolution and will not remain in their current configuration indefinitely. On timescales of millions to hundreds of millions of years, the ring system as it currently exists will change substantially. New material from disrupted moonlets or meteorite impacts may replenish some rings, others may disperse. The relationship between the ring particles and the shepherd moons will evolve as the moon's orbits gradually migrate under the influence of tidal interactions with Uranus. The rings we observe today are a current snapshot of a dynamic system, not the same ring system that existed a billion years ago, not the ring system that will exist a billion years from now. And the moons that maintain them, and the dozens of other moons that orbit Uranus in their own extraordinary configurations, constitute a system of worlds as varied and scientifically rich as any collection of satellites in the solar system. Worlds named for the characters of Shakespeare and Pope, worlds with surfaces that range from the darkest in the solar system to the brightest, worlds with geological features that planetary scientists are still working to explain, worlds that, from the single spacecraft flyby that gave us our only close-up view of them, revealed themselves to be genuinely extraordinary. In one of them, the smallest of the 5 large moons, the innermost of the classical satellites, the moon that perhaps more than any other in the solar system looks like it should not exist in the form it does, is waiting just ahead of us in our journey. Names carry history. The moons of most planets in the solar system were named according to a tradition established in the earliest days of telescopic astronomy, drawing from the mythologies of Greece and Rome, the same classical sources that named the planets themselves and most of the features visible on their surfaces. Jupiter's large moons are named for figures from Greek mythology who had relationships with Zeus. Saturn's moons carry the names of Titans and other figures from the same tradition. Mars's 2 small moons are named for the sons of Ares, the Greek god of war. The naming convention is consistent, predictable, rooted in the same cultural tradition that shaped Western astronomy from Galileo to the space age. Uranus broke the pattern. When William Herschel discovered the first 2 moons of Uranus, Titania and Oberon, found in 1787, 6 years after his discovery of the planet itself, he did not reach for Greek or Roman mythology. He reached for literature, specifically for the works of William Shakespeare, drawing the names Titania and Oberon from A Midsummer Night's Dream, where they are the queen and king of the fairies. The tradition Herschel established has been maintained ever since. Every moon of Uranus is named for a character from the works of William Shakespeare or Alexander Pope. Not a single Titan, not a single Olympian deity, not a single figure from the classical mythology that dominates the nomenclature of the rest of the solar system. Ariel from The Tempest in The Rape of the Lock, Umbriel from The Rape of the Lock, Miranda from The Tempest, Caliban from The Tempest, Puck from A Midsummer Night's Dream, Prospero, Sycorax, Setebos, Stefano, Trinculo, all from Shakespeare, Belinda from Pope, Margaret, Ferdinand, Perdita, Mab from various Shakespearean plays. Orbiting the tilted ice giant, rolling sideways through the outer solar system, is a system of moons populated entirely by characters from English literature. It is one of the more quietly charming incongruities in the otherwise rigorously classical nomenclature of the solar system. Uranus has 28 known moons, a number that may grow as observation technology improves and fainter. Smaller satellites are detected in the planet's outer orbital regions. They range enormously in size and character. The five largest, Miranda, Ariel, Umbriel, Titania, and Oberon, were all known before the space age, discovered through Earth-based telescopic observation, and constitute the classical Uranian moon system. The remaining 23 known moons are substantially smaller, most of them discovered during or after the Voyager 2 flyby, several detected in the years following the flyby through careful analysis of Voyager 2 imagery and subsequent Hubble Space Telescope observations. The smaller moons, the inner moons orbiting close to the ring system, and the irregular outer moons orbiting far from the planet in inclined or retrograde orbits, are mostly dark, irregularly shaped objects whose surfaces tell relatively little at the resolution with which they have been observed. Some of them are almost certainly captured bodies, objects from the outer solar system that strayed too close to Uranus and were gravitationally captured into orbit. But the five classical moons are a different story entirely. Each of them is a world in its own right, with a distinct geological history, a distinct surface character, and a distinct set of scientific puzzles that the brief Voyager 2 flyby illuminated without fully resolving. Titania is the largest moon of Uranus, approximately 1,578 kilometers in diameter, making it the eighth largest moon in the solar system. Its surface shows a geological history of considerable complexity. Long, branching canyon systems, faults and graben structures created when the moon's interior froze and expanded, stretching the surface crust until it cracked, extend for hundreds of kilometers across the terrain. Impact craters of varying ages are distributed across the surface, some fresh and sharp-edged, others degraded by subsequent geological activity that modified the landscape after the craters formed. The canyon systems on Titania are particularly striking. Graben linear depressions bounded by fault scarps on either side, formed when a section of crust drops downward as the surrounding terrain pulls apart, imply that Titania underwent a period of tectonic extension. On Earth, similar features form in regions of crustal stretching. The East African Rift is a terrestrial analog, though operating under different conditions and driven by different forces. On Titania, the extension is thought to have been driven by the freezing and expansion of liquid water in the interior. As water ice occupies approximately 9% more volume than liquid water, the freezing of an internal ocean would have expanded the moon's interior and stretched the overlying crust into the network of graben, now visible on the surface. This implies that Titania once had a liquid water interior, a subsurface ocean, maintained by the residual heat of formation and radioactive decay that has since frozen. Whether any liquid water persists today in Titania's interior is unknown. Current models are uncertain whether the present-day interior temperatures are sufficient to maintain liquid water, or whether the entire interior has now frozen solid. Oberon, the second largest and the outermost of the five classical moons, presents a surface dominated by ancient, heavily cratered terrain. It is the most heavily cratered of the large Uranian moons, its surface showing less evidence of geological resurfacing than Titania or Ariel, suggesting that whatever internal activity occurred in Oberon's history ended earlier and was less extensive than on its siblings. The ancient, battered surface has been accumulating impact craters for much of solar system history, with relatively little internal geological activity to erase them. But Oberon has one feature that stands out even against its heavily cratered backdrop, a mountain rising approximately 6 kilometers above the surrounding terrain, visible as a bright peak on the limb of the moon in Voyager 2 images. The mountain has no official name, but its existence implies that Oberon's crust has the structural rigidity to support significant topographic relief, a crust thick and cold enough not to have flowed viscously and smoothed out the mountain over geological time. The dark floors of many of Oberon's large craters are another feature that attracted scientific attention during the Voyager 2 analysis. Some craters have floors that are noticeably darker than the surrounding terrain, suggesting that dark material welled up from the interior and flooded the crater floors after the impacts that formed them. This dark material may be a mixture of water ice and carbonaceous compounds from the interior, suggesting that even a relatively inactive moon like Oberon experienced some post-impact volcanic or cryovolcanic activity. Ariel occupies a fascinating middle ground in the geological spectrum of the Uranian moons, showing more evidence of geological activity than Oberon or Umbriel. but less than the extraordinary geological complexity of the moon we will examine in detail in our next section. Ariel's surface is the brightest of the 5 classical Uranian moons, its high albedo suggesting a surface composition rich in relatively uncontaminated water ice, perhaps fresher and less radiation-processed than the darker surfaces of Oberon and Umbriel. The brightness itself is a geological clue, a surface that has been recently resurfaced by water ice erupting from the interior, covering older, darker terrain with fresh, bright material. The geological features on Ariel's surface support this interpretation. Extensive valleys, some of them several hundred kilometers long and up to 10 kilometers deep, cut across the terrain, with floors that are notably smoother than the valley walls and the surrounding cratered landscape. These smooth valley floors appear to have been flooded by viscous material that erupted from the interior and flowed along the valleys before solidifying, a process called cryovolcanism, where a mixture of water, ammonia, and other volatiles behaves as a volcanic fluid at the low temperatures of the outer solar system. Ariel appears to have been one of the most geologically active of the Uranian moons in its history, a world that experienced significant cryovolcanic resurfacing, perhaps maintained by tidal heating from its orbital interactions with other moons, that has since largely quieted. Umbriel stands in stark contrast to its neighboring moon Ariel. Where Ariel is bright and geologically complex, Umbriel is dark and ancient-looking, the darkest of the 5 classical Uranian moons, its surface covered in uniformly old, heavily cratered terrain that shows almost no evidence of the resurfacing and geological activity visible on Ariel, Titania, and Miranda. The darkness of Umbriel's surface is striking. Its albedo, the fraction of sunlight it reflects, is approximately 0.26, considerably lower than Ariel's 0.53 or Miranda's 0.32. This low reflectivity suggests that Umbriel's surface is coated in dark, radiation-processed material, the kind of carbonaceous residue produced by billions of years of particle and photon bombardment, working on originally icy surface material. There is one conspicuous exception to Umbriel's dark uniformity. On the floor of a large crater designated Wunda, there is a bright ring, a circular feature significantly more reflective than the surrounding dark terrain, standing out like a spotlight on an otherwise dim surface. The nature of this bright ring is not well understood. It may be a deposit of bright material erupted from the crater floor after the impact, a small-scale cryovolcanic event. It may be a particularly fresh impact that excavated bright, unprocessed ice from beneath the dark surface layer. It may be something else entirely. Umbriel's Wunda ring is one of the minor mysteries of the Uranian system, a small, bright anomaly on a dark and ancient surface, noticed but not explained by the single spacecraft that has visited it. What made the Uranian moon system so fascinating to the Voyager 2 scientists who first examined the returned images was not simply the individual character of each moon. It was the pattern, the systematic variation in geological activity and surface brightness that seemed to correlate with orbital position and size in ways that implied a coherent history of the entire moon system. The innermost large moon, Miranda, showed the most dramatic and unexpected geology. Ariel, next outward, showed extensive geological activity. Umbriel showed the least. Titania and Oberon, the outermost and largest, showed intermediate levels of activity consistent with their larger sizes, providing more internal heat from radioactive decay. This pattern, inner moons more geologically modified, outer moons more ancient and cratered, is broadly consistent with a scenario where tidal heating from Uranus played a role in the geological history of the inner moons. A moon orbiting close to a large planet experiences stronger tidal forces. Its interior is repeatedly flexed by the changing gravitational gradient as it orbits, generating heat through internal friction. The closer the moon, the stronger the tidal flexing, and the more heat is generated. Tidal heating from Uranus, supplemented by radioactive decay in the rocky components of each moon's interior, could have driven the geological activity observed on Ariel and Miranda while leaving the more distant moons, Umbriel, Titania, Oberon, less thermally active and therefore less geologically modified. But tidal heating alone is not sufficient to explain the most extraordinary feature in the entire Uranian moon system, the feature that, when Voyager 2's cameras first resolved it in January 1986, produced genuine astonishment in the scientists examining the data. Miranda's terrain. A surface so geologically bizarre that it seemed, at first examination, as though someone had taken several completely different worlds and assembled them randomly on a single moon, like a geological jigsaw puzzle whose pieces had been shuffled and reassembled without regard for whether they belonged together. Nothing in the prior experience of planetary science had prepared anyone for what Miranda looked like up close. There is a moment in scientific discovery that has no good name. It is not the moment of understanding that comes later, after analysis and modeling and the slow accumulation of explanatory frameworks. It is not the moment of mere surprise. Surprise implies that the unexpected thing fits somehow within an existing category, that it is unusual but comprehensible. This moment is different. It is the moment when something appears in front of you that your entire background in a field has not prepared you to interpret. When the data arrives and the immediate response is not, "Oh, interesting," or "that is unexpected," but something closer to "what is that?" Scientists who were present in the Voyager 2 mission control room in January 1986, watching the images of Miranda resolve from blurry pixels into detailed photographs as the spacecraft made its closest approach, described something close to that moment. Miranda was supposed to be a small, geologically simple moon. It is tiny, only approximately 472 kilometers in diameter, less than a third the diameter of Earth's moon, small enough that early planetary scientists assumed it would be a simple, geologically dead body covered uniformly in ancient impact craters, its interior long since cooled and frozen, its surface a record of nothing more interesting than the bombardment history of the outer solar system. What appeared on the screens in January 1986 was not that. Miranda's surface, at the resolution Voyager 2 could achieve during its closest approach, is one of the most geologically complex and diverse surfaces of any comparably sized body in the solar system. The moon appears to be assembled from distinct regions of fundamentally different terrain types, geological provinces so different from each other in character, age, and structure that they seem, at first inspection, to belong to entirely separate worlds. Ancient, heavily cratered terrain of the kind, expected for a geologically simple body, sits alongside regions of younger, more complex geology in a juxtaposition that implies a history far more eventful than Miranda's small size would suggest. The most visually dramatic features on Miranda are the coronae, large, roughly oval or trapezoidal regions of highly deformed terrain, marked by parallel ridges and grooves arranged in concentric or chevron-like patterns that create a striped appearance quite unlike the impact craters and random fractures that dominate most lunar surfaces. 3 major coronae have been identified: Arden, Elsinore, and Inverness, all named for locations in Shakespeare's plays. These coronae are unlike anything found on any other moon in the solar system. Their parallel ridge structure, their sharp boundaries against the surrounding ancient terrain, and their geological freshness relative to the cratered regions around them, all indicate that they formed through some process distinctly different from the impact cratering and simple freezing that characterize most of Miranda's surface. What process? That question remains genuinely open, debated, with several competing hypotheses that the available data cannot fully discriminate between. The most dramatic single feature on Miranda, and one of the most extraordinary geological features in the entire solar system, is a cliff. Verona Rupes, named for the setting of Romeo and Juliet, is a fault scarp on Miranda's southern hemisphere that drops approximately 20 kilometers from its upper rim to its base. 20 kilometers of vertical relief on a moon only 472 kilometers in diameter. To put that in perspective, the tallest mountain on Earth, Everest, measured from sea level, is approximately 8.8 kilometers high. The deepest point in Earth's oceans, Challenger Deep in the Mariana Trench, reaches approximately 11 kilometers below sea level. Verona Rupes, on a moon smaller than many terrestrial countries, presents a cliff face roughly twice as tall as Everest above its base. If you stood at the top of Verona Rupes and dropped a rock off the edge, it would take approximately 10 minutes to reach the bottom, falling in Miranda's weak gravity, only about 0.8% of Earth's surface gravity, in a long, slow arc that would carry it a significant horizontal distance before it finally struck the base of the cliff. A human being falling from the top of Verona Rupes in a spacesuit would survive the fall. The weak gravity means the terminal velocity reached over 20 kilometers of free fall would be comparable to a survivable fall on Earth. The tallest known cliff in the solar system, on one of the smallest moons, orbiting a sideways rolling ice giant in the outer reaches of the solar system. The universe does not arrange things for human convenience or human aesthetic preference, and yet occasionally it produces something like Verona Rupes, a feature so extreme, so far beyond the ordinary scale of planetary geology that it seems almost deliberate in its impressiveness. Verona Rupes is a fault scarp, a surface formed when one section of Miranda's crust dropped relative to the adjacent section along a fault plane. The extreme height of the cliff implies an extreme amount of fault displacement. The two sections of crust moved apart vertically by approximately 20 kilometers, a displacement that required the interior to have accommodated significant deformation. The orientation of Verona Rupes and the overall pattern of faulting in Miranda's southern hemisphere suggest that the moon experienced a period of extensional tectonics, its crust being pulled apart rather than compressed together, similar in broad mechanism to the Graben formations seen on Titania, but more extreme in both scale and visual drama. The extension that produced Verona Rupes likely resulted from the freezing and expansion of liquid water in Miranda's interior, the same mechanism proposed for Titania, but on Miranda, the expression of that expansion is more visually concentrated and more topographically spectacular. Why Miranda's extensional tectonics produced a cliff of such extreme height, rather than the network of Graben valleys found on Titania, is not fully understood. The specific geometry of the fault, the angle of the fault plane, the composition of the rock on either side, the rate at which the displacement occurred, would all have influenced the morphology of the resulting scarp. The details of that geometry are constrained only loosely by the Voyager 2 imagery. Return now to the coronae, those extraordinary oval regions of parallel ridges and grooves that make Miranda look, in certain views, like it has been decorated with enormous geometric patterns. Several hypotheses have been proposed for how the coronae formed, and the scientific community has not reached consensus on which is correct. The most straightforward hypothesis, sometimes called the disruption and reassembly model, proposes that Miranda was struck by a large impactor early in solar system history, catastrophically disrupting the moon into fragments, which then fell back together under their own gravity in a disordered reassembly. The coronae would, in this scenario, represent regions where material from different depths within the original moon ended up juxtaposed at the surface. Interior material exposed alongside surface material, compositionally mixed terrain that explains the distinct geological provinces. This hypothesis has the appeal of not requiring any exotic geological processes. Catastrophic disruption of small icy bodies is not unprecedented in the solar system, but it faces challenges in explaining the specific geometry of the coronae, the parallel ridged structure, the sharp boundaries, the consistent orientation of ridges within each corona. These features are not obviously the products of a disordered reassembly. An alternative hypothesis proposes that the coronae are the surface expressions of upwelling from the interior, regions where warm, partially melted material rose through Miranda's ice rock mantle and spread laterally under the surface crust, deforming the overlying terrain into the ridged patterns observed. This is essentially a cryovolcanic upwelling model, Miranda's interior, heated by tidal forces or radioactive decay, driving convective upwellings that deform the surface from below without necessarily erupting through it. This hypothesis explains the geometric regularity of the coronae more naturally than the disruption model. Upwelling plumes beneath a thin surface crust would naturally produce oval or circular regions of deformation, with the kind of concentric or parallel ridge patterns observed. But it requires Miranda to have been significantly warmer in its interior than its small size would easily explain. The heating mechanism for Miranda's geological activity is itself one of the outstanding puzzles of the Uranian system. Miranda is small enough that the heat of formation and the heat generated by radioactive decay in its rocky component should have been lost to space relatively quickly in geological terms. A body of Miranda's size, without any additional heat source, should have been geologically inactive for most of solar system history. But Miranda's surface is clearly not simply the product of an ancient, inactive body. The coronae are geologically young relative to the ancient cratered terrain. Their low crater density indicates they formed after the period of heavy bombardment, meaning they are geologically recent features whose formation required an active geological process operating well into solar system history. Where did the heat for that activity come from? The leading candidate is tidal heating, the same mechanism proposed for Ariel's geological activity, where the gravitational flexing of the moon's interior by the tidal forces of Uranus generates heat through internal friction. Miranda, as the innermost of the 5 classical moons, orbits closest to Uranus and therefore experiences the strongest tidal forces. Current tidal heating models for Miranda's present orbit suggest that the tidal heating rate is insufficient to maintain the level of geological activity recorded on the surface. To explain Miranda's geological history through tidal heating requires either that Miranda's orbital properties were different in the past. Perhaps it was caught in a resonance with another moon that amplified the tidal heating, or that the tidal heating rate is being underestimated by the current models. The most favored scenario involves an orbital resonance, a configuration where Miranda's orbital period was a simple fraction of another moon's orbital period, causing the gravitational interactions between the moons to periodically reinforce each other and amplify the eccentricity of Miranda's orbit. A more eccentric orbit means larger tidal deformations, as the distance between Miranda and Uranus varies around the orbit, and larger tidal deformations mean more frictional heating. This resonance, if it existed, has since been disrupted. The moons are not currently in the resonance configurations that would have been responsible for the enhanced heating. The geological activity it drove has largely ceased. Miranda's surface is the frozen record of a period of tidal activity that has now ended, its coronae and its extraordinary cliff preserved in the cold of the outer solar system. Miranda was observed by Voyager 2 more closely than any other Uranian moon. The spacecraft's trajectory carried it to within approximately 29,000 kilometers of Miranda's surface, closer than its approaches to any of the other classical moons. This fortunate geometry meant that Miranda was imaged at higher resolution than its siblings, allowing the geological complexity of its surface to be resolved in greater detail. Even so, only the southern hemisphere of Miranda was illuminated during the Voyager 2 flyby. The northern hemisphere was in winter darkness, part of the 42-year polar night that affects all bodies in the Uranian system, sharing the planet's extreme axial tilt. The northern hemisphere of Miranda has never been directly imaged. Whatever geological features it contains, whether the coronae and the tectonic complexity of the south extend into the north, or whether the northern hemisphere is geologically distinct, is unknown. Half of one of the most extraordinary geological surfaces in the solar system has never been seen. What it looks like is a question only a future mission to Uranus could answer. Miranda, in its combination of geological complexity, topographic extremity, small size, and partially unobserved surface, represents one of the most compelling individual targets for future solar system exploration. A world that should have been simple and turned out to be the most geologically bizarre moon of its planet. A world with the tallest known cliff in the solar system, surface features unlike anything found elsewhere, and a geological history that existing models cannot fully explain. A world half of whose surface has never been seen. And the spacecraft that gave us the glimpse we have of Miranda, that flew past the entire Uranian system in a matter of hours, collecting data at a pace determined by the speed of light and the finite capacity of 1980s electronics. That spacecraft made its closest approach to Uranus on January 24, 1986, and was past the planet within hours, carrying its instruments outward toward Neptune and eventually toward the edge of the solar system. It was the only visit we have ever made, and it lasted an afternoon.